Hello, I'm Jim Salisbury with Mitsutsuya America Corporation, and welcome to the Metrology Training Lab. In this episode, we're going to talk about the calibration of calipers. In past episodes, we've defined the concept of calibration, discussed the purpose of calibration, and introduced important aspects of what makes a good calibration method. In this episode, we'll apply all those ideas to the calibration method for a caliper. Calibration is a search for errors, and we want to develop a calibration method that efficiently hunts down and finds any potential errors in the measuring instrument. So how do we best do that for a caliper? Well, there's a nice American national standard for digital, dial, and vernier calipers called ASME B89.1.14. And the calibration method that we'll be discussing is based on that standard. Calibration usually starts with checking out the proper operation of the caliper. Is there any obvious damage? Does it move smoothly? Do the buttons work correctly? And once you're satisfied with the operation, then we begin the accuracy tests. On calipers, the conditions of the measuring jaws over time is always a concern. For the external measuring faces, before you begin measuring anything, you bring the measuring faces close together, but not touching, and then look at the gap between them in front of a light. This may look silly, but it actually works. The use of the light gap is an efficient way to see any wear or bending of the jaws. If you see something, you can then do a more thorough and quantitative test by using a gauge pin. This is done by simply moving the gauge pin from near the beam to the tips of the jaws while observing the readings. Here all the values are 0, so we know that the flatness and parallelism of the jaws are in good shape. The use of a light gap is also good for checking the condition of the internal measuring faces, in particular when you have the crossed knife edge type like we have on this caliper. To check these internal measuring jaws, you don't create a gap, but instead you close the calipers and then slightly rotate it and look at that gap at an angle to check the condition of the measuring faces. Again, you might think I look silly, and looking at gaps of light might not feel too scientific, but it has been proven over and over to work pretty well. The very common caliper, like this one here, has 4 different types of measurements it can make. And therefore our calibration method needs to be properly engineered to sufficiently and most efficiently hunt down the potential errors. As already mentioned, this caliper can make both outside and inside measurements. Most calipers like this, up to 12 inches, also have some type of depth bar for making measurements into holes or slots. The 4th type of measurement that's possible with this caliper is the step measurement, which uses these 2 faces to make measurements like this step height on this cylindrical workpiece. This type of caliper is quite common, so we will discuss the necessary accuracy tests to calibrate this caliper. There are other configurations of calipers out there, and after watching this episode, you should be able to extend what we discuss to the calibration of all types of calipers. For all of our measurements, we will want to properly use the caliper. The most important skill in calibrating calipers is simply using it correctly. If you're having some struggles getting good results, find yourself a caliper that's known to be in good condition, grab some reference standards, and practice. It doesn't take too long to get the right feel. The general principle of the calibration method, which is based on the requirements of the ASME B89.1.14 standard, is that all 4 measurement methods, outside, inside, depth, and step, all use the same measuring scale. In addition, the 0 point is only set once, based on the outside measuring faces. And so from all that, the calibration method is to measure multiple points across the measuring range using the outside measuring faces, and then only a single test point with each of the other measuring faces. Now let's look at this method more carefully. First, we will clean all the measuring faces, and then bring the outside measuring faces together to set our 0. We will double check our 0. But when we're done with that, we won't change it again during the calibration. The first test is with the outside measuring faces. For a 6-inch caliper, the ASME standard requires a minimum of 3 points across the measuring range. The minimum then increases for larger calipers. We will take 4, as that is convenient for the reference standard that we're using, which is this Metrology caliper checker. This is a nice standard for calibrating calipers, but you could use any grade or material gauge block as well. We'll start at 1 inch. In accordance to the ASME standard, the length specifications apply at any point across the measuring faces, thereby including any influence of the jaw parallelism. During the calibration, it's important to intentionally vary the distance from the beam at different test points. At the 1-inch point, I'll start close to the beam and report that value. I'll also check it further out just to see if the caliper may give me some problems. When using or calibrating a caliper, it's important to learn how to get a consistent value. The amount of force you apply can vary the results. As you see here, I am applying too much force, and the values change by several thousandths of an inch. So don't do that. Alignment is also a problem. If you're misaligned in this direction, you can see the values get larger. If you are misaligned in this direction, again, the values get larger. So you want to rock the caliper in both directions while applying a consistent force and looking for the smallest value. It looks like the error at this test point is -0.5. So I'll write that down. It's understood that when using a caliper, you need to rock it around a bit to get the proper result. This applies to normal use as well as in calibration. It's not correct, however, to take a bunch of readings and report the average values during the calibration. The caliper should be repeating within the specification limits for the length accuracy. And if not, then the caliper should be rejected. It is also not correct to rock it around until you get the value you like, right? This digital caliper has a resolution in inches of 1/2 thou or 5/10. In metric, the resolution is 10 microns. And if you don't understand a thou or a tenth or microns, go watch our episode of the Metrology Training Lab that discusses the units of measure. For this size digital caliper, the tolerance is ±1/1000th of an inch for all the test points that we're taking, including the outside, inside, depth, and step. Caliper specifications can be tricky to understand. I recommend you review the technical bulletin we put together on this topic. You can find that on our on-demand educational website. So let's continue with the other test points. At 2 inches, I'll measure about halfway down from the beam to the tips of the jaws. After some rocking around, the air looks to be -5/10. Moving to 4 inches, the air also looks to be -5/10. At 6 inches, I'm going to measure out near the tips of the jaws. I need to be very careful here with my force. I'm applying too much force there. That feels better. After a little wiggling around, once again, the air looks to be -5/10. This completes the testing of the outside measuring faces. An alternative to the caliper checker is to use gauge blocks. That's fine, but be careful. You need to measure them like this, because you need to move across the jaws like we showed with the caliper checker. You can't measure them like this. You want to ensure your test method is sensitive to the parallelism of the jaws. It's tempting to measure the gauge blocks across the entire measuring faces. That's easier. Or maybe to measure them only near the beam. That's usually less influenced by your force. However, it's not our job to calibrate the caliper in only its easiest or best mode of use. On the contrary, we need to assess its accuracy across any reasonable and likely use. Now let's move to the inside measuring faces, and we will use this caliper checker again. If you don't have a caliper checker, a ring gauge like this is a good solution as well. As mentioned before, you only need a single test point, and the ASME standard states the size to be somewhere between 3/4 of an inch and 2 inches. The technique for inside measuring faces is a little more difficult. If you rock this way, the values get smaller again. But if you rock this way, they get larger. So you need to wiggle this way, looking for the smallest value, all while applying a constant force, and then wiggle this way, looking for the largest value. Looks like I'm getting -5/10. This caliper has crossed knife edge inside measuring faces. They are sharp, but of course there is still some thickness to these edge faces, and there's some gap between the two edges. It's pretty well known that if you measure a small inside diameter, that you may measure undersize when using the cross knife edge measuring faces. This is particularly a problem when there is some damage to the faces, so it's valuable to check this during calibration. This is done by using a small ring gauge, like this ceramic setting ring. The ASME standard specifies a 0.2 inch diameter for this test, like we have here. Now measuring this ring gauge is pretty easy. Just apply a good consistent force and wiggle it around a little bit. Looks like I'm measuring minus a thousandth of an inch. For the last two measurements in the calibration, we'll use a gauge block placed on this surface plate. For both the depth and step, the ASME standard specifies a single test point less than 2 inches. So we'll use this 1-inch gauge block. Here at Metrology, we like square blocks for the depth measurements for obvious reasons. In this case, I measure an error of plus 5/10. So we'll write that down. Lastly, we do the step measurements. Again, a square gauge block works well. We'll use the same 1-inch gauge block. We can hold the caliper against the block and simply take our reading. Looks like the error is minus a thousandth of an inch. So we'll write that down. So this completes the calibration. All the errors here are within the plus or minus 1/1000th of an inch specification. So it looks like this caliper is in tolerance. And that's the calibration of calipers. Remember, the method we just discussed comes from the American National Standard on Calipers, ASME B89.1.14. Lots of experts from around the country help write this document, but the B89 committee is always looking for ideas to improve the standards. Metrology America is heavily involved with this committee, and if you would like to post comments on this standard, good or bad, we'd gladly bring them to the committee's attention. The standards committees are also open to the public, and you're welcome to attend. Thank you. I'm Jim Salisbury, and I'll see you next time from the Metrology Training Lab.